All right, so today on this part of the lesson, we're going to be looking at function transformation. So, function transformation is essentially the idea that you take a function that already exists and you just change it around a little bit. So, you move it left, right, up, down, you squish it or stretch it in certain ways, and in doing that, you will receive a new function. So, let's just take a peek at kind of what that looks like real quick. So, if we look over here, so let's say we have the function f of x, okay? So if we have f of x, so let's just say f of x looks like this, right? Okay, that's fair enough. So this is the original function, whatever it is, it looks like that. So if we were to do another function that looks exactly like it, but this function were a little bit to the left, so we just take this function, move it a little bit to the left, that would be a function transformation. So this function is the same as this other one, it's just that it's been moved to the left a little bit. I could also do the same by moving it to the right a little bit, or moving it up a little bit, or moving it down a little bit, or doing it, but, a little bit shorter. So let's say I did a little bit shorter. Oh, wait, that was shorter. That was silly. Okay, so now a little bit shorter, or a little bit wider. All of these would count as function transformations because it's just the original with a couple of things changed around. So let's go ahead and leave that there for now. We'll come back to that. So that's the idea of function transformation. That's how they work. So we're going to talk about shifts. So shifting a function means that we're moving it up, down, left, or right. So there are these things called parent functions. So parent function just refers to the original form of a function. So let's go back to the board real quick. And so over here, so let's say our original function is x squared. So I'm going to put parentheses on x squared. So x squared naturally is like this. So this is, that's just x squared. That's just the way it goes. So what we can do is we can do little bitty shifts to the equation to make it different. So let's say we have g of x, and g of x is equal to x squared. And let's say that we add 1. So if we add 1 to the y value, that means it's essentially the same function, except it is shifted up a bit. So it's the same function, but we've moved it up a teeny bit. So you can always move it up by adding after, outside of the parentheses. So the parentheses I put around x. So if you add outside of those, you can move the function up. And the opposite is true if we move the function down. So if instead of doing the adding, so instead of adding 1, we subtract 1. Instead of going up, we are going to go down 1. So then we would go right here and boop, boop, and there you go, the function just like that. We have just moved it up or down. So adding and subtracting outside of the parentheses, that moves it up and down because we're just directly adding or subtracting from the y value. And the y value is, of course, the height. So whenever we do adding and subtracting on the outside, that's going to move us up or down. So now let's clear these out a little bit. Let's redraw the good old f of x. So f of x is like this. Or, well, my drawings are not exactly to scale. So, I would recommend playing around with Desmos to play around with a couple of these so you can get used to how they shift. So, but real quick, while we're here, let's go ahead and do g of x. So let's say g of x. So instead of adding or subtracting on the outside, let's say I want to add and subtract on the inside. So if I put x minus 1 on the inside, now you might be thinking to yourself, oh, okay, so when we subtracted 1 on the outside, we moved down. So if we're subtracting 1 on the inside, probably going to move left or right. So when we subtract 1 on the inside, we actually move to the right one. So this is very important. So whenever we're inside the parentheses, the rules are basically opposite of what they used to be. So normally, we would think of moving right as a positive thing. But in actuality, when we're looking at our function, we need to subtract 1 in order to move right. So basically, we're making the x value need to be bigger before it's doing the same things it used to. So for instance, if I have, let's say I have 2 square, that would give me 4. So if I, however, subtract 1 from it, well, now that's only going to give me 1. So I actually need to increase 2 to 3 before I actually start getting 4 again. So by subtracting 1, I've actually shifted my x values to the right one. I need to go further to the right in order to get the same values that I used to get. And this is why subtracting on the inside of a function causes it to move to the right, which is perfectly fine. So from here on out, anytime we're subtracting inside the parentheses, so inside the parent function, that is going to be a move to the right. So since subtracting inside the parentheses moves us to the right, as you could probably guess, adding on the inside actually moves us to the left. So if we were to do x plus 1 square, so we'd move 1 to the left, and then we'd have the same function. It's supposed to be the same function. So whenever we are subtracting on the inside, that tells us how far to go right. And whenever we are adding inside the function, that tells us to go left. So let's do a quick example of shifting, but with without me telling you what the parent function is. Let's see if you can guess it. If not, that's okay. We're just going over examples right now, and there are plenty on the independent practice. So let's say we've got g of x is, let's say we've got absolute value of x plus 2 minus 1. So real quick, in red, the parent function here is going to be the absolute value of x. Now, it's been a little bit before since we've looked at the absolute value of x. So real quick, I'll graph it in red. So the parent function is just that. So it looks just like that. So I want you to go ahead and pause the video and guess what we're going to have to do in order to draw g of x. So we're starting off with f of x. Where do we have to move in order to get our new video? Did you guess? Okay, cool. Let's check that guess. So according to this, so it's plus 2. So we're moving 2 to the left. And it's minus 1 on the outside. So that's going to tell us to move 2 down. So we're going to go 2 left and down 1. So right here. And then we're just going to draw the same function. So yeah, so we're just shifting it around. This is how shifts work. They just move you around a little bit. So beyond that, that's all they really do. So that shifts in a nutshell. But that's just adding and subtracting. You might be thinking to yourself, well, wait a minute. Does that mean we're going to have to do multiplication and division? And yes, it does. So let's go ahead, switch back over. Now we're going to look at stretches. So we're going to look at 2 different kinds of stretches. Stretches and squishes. So we're going to look at vertical stretches first, because I think vertical is the one where everybody's on the same page. It's like, oh, it's a vertical stretch. We know what those look like. So let's go to the board. Okay, so let's say we got f of x equals, let's say it's, what do we want to do? Let's use absolute value of x this time. So absolute value of x, so the x is inside the parentheses for this. So as we stated before, it goes like that and it goes like that. So pretty easy, pretty straightforward. So now let's look at what happens when I multiply by a number on the outside of the parentheses. So let's say I put a 3 right here. So if I put a 3 right there, so that's outside the parentheses, so it's outside the absolute value. This function is going to get a lot taller. It's going to get a lot taller. It's almost as though I just grabbed the ends of this and I just pulled them up. I just pulled them up. I just stretched it as though I wrote it on like a piece of paper, and then I just stretched that paper so that that goes up. This is known as a vertical stretch. So if you multiply by a number on the outside, that is a vertical stretch. So if you multiply by a number that's bigger than 1 on the outside, it's a vertical stretch. And I say bigger than 1 because if you multiply by 1, nothing really changes. But if you multiply by a number bigger than 1, it's like it gets pulled up. You're pulling it up. You're stretching it up. Meanwhile, if we try to do the opposite of that, so let's say we have h of x, and that is 1/3 absolute value of x. So instead of multiplying by 3 on the outside, I'm dividing by 3 on the outside. Because 1/3, that's the same as divide by 3. Those two are the same things. Multiply by 1/3, divide by 3, same thing. So we're multiplying by a number that is lower than 1, but it's not negative. So if we multiply by a number that's lower than 1, we're actually going to make it much wider. So it gets much wider. And it's almost as though we are squishing down the equation. So rather than, writing it on a piece of paper and pulling that paper up, we're pushing the ends of that paper together. On the top and bottom, we're pushing it together. It's getting squished back down. So this is called a vertical shrink. So a vertical shrink or a vertical compression. So vertical compression. It gets said either way. Know that just shrink and compression mean the same thing. And so the factor by which you will stretch or compress is always the number in front. So the number in front is always the factor that you're using. So factor. So if we wanted to get from F to G, we would do a vertical stretch by a factor of 3. And if I wanted to get from F to H, I would do a vertical compression or vertical shrink by a factor of 1/3. So I'm making it 1/3 as tall as it used to be. So that would be how we describe that in English. So it's a stretch and compress using the vertical. So we're just pulling it up or pushing it down. So that would be the way that goes. So with that said, let's go ahead and clean this up. So you might be wondering to yourself, wait a minute, that's vertical. Does something happen with horizontal? Well, yes, it does. And which one is happening depends on where we are. So real quick, let me go back and we'll switch slides. So all of this is happening outside of the function. So it's happening outside of the parentheses. Meanwhile, we have horizontal stretches and squishes. Horizontal stuff happens inside the parentheses. So you may have recalled earlier when I said that inside the parentheses, the rules are backwards. That also applies to stretches and squishes. So let's say I've got e to the x. This is one that tends to bother some people. So I'm going to go ahead and write it as e to the x. So let's say this time that, so instead of them being on, so instead of them being on the outside, we're going to put it on the inside. So we'll put 3x right there. Okay. So if we were doing a vertical stretch would look like 3 times e to the x. So the 3 would be outside of parentheses. Outside of the parentheses is always vertical, whereas inside the parentheses is going to be horizontal. So right now we're talking about horizontal, so we're talking about inside those parentheses. So inside of those parentheses, that's what we've got. We've got a e to the 3x. We're going to focus on that right now. So we got e to the 3x, and so let's go ahead and draw these. Let's see what these look like. So in case you're not familiar with the e to the x function, the e to the x function basically looks like, oh, it doesn't touch there though. So it basically looks like that. Okay, and now let's look at 3 to the x. So normally with vertical stretches anyway, so with vertical, if we multiply by a number bigger than 3, then we stretch it vertically. It's as if we grab the top and bottom of the piece of paper and we pull. So horizontal is going to be the opposite. So instead of a big number making us stretch, a big number is actually going to make us squish. So we're gonna squish this down so that it's actually squished. It's as if we grabbed the function and then we pushed it towards the center. We grab both ends and we push them towards the center. So anytime on the inside you multiply by a number that is bigger than 1, this is going to be a horizontal shrink or a horizontal compression. So shrink or compression. So if on the inside you're multiplying by a big number, that actually means that you're grabbing the edges of the paper and you're pushing them together. So the function's being pushed towards the middle on both sides. Meanwhile, if we do the opposite, as I'm sure you've probably guessed, if we were to put something up there, say 1/3 x, then instead of pushing it in, we would be pushing it out. So we're pushing that way and that way. So that one, we are actually going to be out here. So the rules are backwards. So if we're inside the parentheses, big number means squish it towards the middle. If we're outside the parentheses, a big number means pull it away from the center. So remember, outside is vertical stuff. Here, I should probably use yellow. So outside of the parentheses, that's where vertical stuff goes. And inside of the parentheses, that's where horizontal stuff goes. So real quick, I am going to go ahead and I'm going to put an example on the board that we're going to do together that goes over all of these rules at the same time. So let's say for the sake of argument, so let's say f of x is the function x squared. Okay, so that's our original. Not too crazy. We want to graph that. We know what that looks like. It looks like that pretty much. So then let's say we have g of x, and g of x is very different. So let's say we have 3x, let's say we have 3x minus 2 squared plus 5. Okay, so let's tackle these in order. So this plus 5 on the outside means goes 5 up. Fair enough. This minus 2 here means we go 5 right. This 3 means I'm going to have a vertical stretch with a factor of 3. Okay, so if I have a point, so if I have the point at 0, 0, and 0, 0 is always where you want to grab your point. So we're starting at 0, 0, and we got to move. So we got to move 5 up. So we move 5 up, and we move 2 to the right. I don't know why I wrote 5 to the right. That should say 2 to the right. So 2 to the right. My apologies. So we move 5 up and only 2 to the right. So we move 5 up to the right. So we're right about here. Now, this is vertically stretched, so it's going to be a lot taller than the original was. So we go ahead and sketch that. And so this would be what g of x looks like, this red one up here. If you're colorblind, I am so sorry. I will label them. So g of x is up there, f of x is down here. So we basically took that function, moved it up, moved it to the right, and now it's much taller. So that would be an example of 3 out of the 4 function transformations happening all at the same time. Now, I didn't put any numbers inside the horizontal thing because I didn't want it to look even weirder than it already does. I would recommend going to Desmos. Again, Desmos is very good at graphing things quickly. I would recommend going to Desmos so that you can play around with a couple of functions like this. That way you get comfortable with all of the different kinds of function transformations. And you can use whatever function you want. If you just want to use f of x and then fiddle around with putting numbers, add, plus, minus, wherever you want, that'll give you some ideas of how x squared really works. And of course, you could try other functions. You could try e to the x. You could try ln of x. You can try square root of x. These and more, anything you can think of. You are, of course, very welcome to try them all out on Desmos and, of course, with your independent practice. And your independent practice is going to focus more on each individual bit rather than all 4 of them at the same time. But still, it's good practice, and it'll help you understand the material a little bit better. So now let's go back, and I believe that's everything. Yep, so that is everything to do with function transformations. So this example I'm going to leave in the, I'm going to leave this unsolved in this video so that we can go over it in the synchronous hours. So I hope to see you then, and you have a wonderful day. Bye-bye.